In the previous class, we learned about the brief architecture of a solid state drive. It's called SSD. So we already know that the performance of SSD is higher than the performance of HDD, because we also learned about some brief architecture of HDD and then how HDD work in the computer system. So I think you know that. So now you know that HDD use the spindle motors. So it's the mechanical device. So because of this mechanical property of HDD, the performance of HDD is very low. But SSD is the solid state drive. And the SSD use the flash memory as main storage media, and that is the solid state memory device. So that's why the performance of SSD is much higher than that of HDD. So we also learned how the flash memory is managed inside of SSD. So because of native property of this flash memory, the SSD needs to manage flash memories. So usually in the SSD, there are multiple flash memory chips. It's called packages, and then inside of the package, there are multiple also there can be multiple ways also, and then also inside of each package, there are multiple dies and then multiple planes. That is the hierarchy of flash memory. Also, in order to support the unique characteristics of flash memory, such as the impulse write is not supported. So in order to support these native properties, so the flash memory should be managed by firmware. And then this firmware is called FTL, the flash translation layer. So actually, because of this flash translation layer, the SSD has many, the SSD has some research topics. So it's very important research topics. So because based on this FTL management approach, the performance of SSD and then some other metrics such as reliability are also determined. So those are some research topics inside of SSD. Okay. We also learned about the file system. So this file system is another abstractions in computer systems. So actually, that is it is the similar topic of the operating system, because operating system provides some abstraction levels regarding computer hardware such as processors, and then memories like virtual memory, also the file system. So file system is a virtualization of storage devices. And the process, actually the process is the virtualization of CPUs or core. Also the virtual memory is a virtual memory is the virtualization of the memory devices or memory space. So operating system provides these abstractions, because with these abstractions we can use computer systems more conveniently, and because the detailed complexity is hidden below these abstractions. So file system is a virtualization of storage devices. That means that with the file system, we can access the data inside of storage devices, but we do not handle this data inside of storage directly. So actually we can make files that is the some bunch of data, and then we access these files. So if we make a file, then so we can also store our data or some metadata such as some permissions, and then parameters, and then some the access time information can be stored inside of the file. So that's another abstraction of the this storage devices. But in the previous class we learned that files are managed with, it's a normal files such as some normal items, file items, and directories. So multiple files are inside of a directory, but I explained that actually that is the view of a user. Okay, so as a viewpoint of the user, the file and directories are organized like this, like tree-like structures. But actually, files has some plain layer. So that means that each file, well, actually, in the file system, files are included inside of the directory, and then directories are managed like a tree structures. But in reality, the files have plain hierarchy. So that means each file has some pointer. So inside it's called the index node, and then so files are actually stored in these storage devices, and then this index node points the location of the file. Also, directory is just a list of files, and then this directory stores the file name and then file index numbers. It's called the inode number. So this is just a list of list of files inside of the directory. So based on this directory, so when a file is accessed by an application, then the operating system firstly access the root directory. It's called root, and then we can find the list of files or directories inside of this root directory, and then so we can find the final location of our target file based on these structures, the list of structures inside of root directory, and then some lower level of the directories. Okay. So we learned about the basic file systems, and then so in this time, so let's discuss how files are stored inside of storage devices. Okay, so we learned that if we generate the file, so these files will be included inside of the directory, and then so that means that this new file is registered the list of a directory. And when the file is generated, the operating system also modifies this file system. So that means that the index of the file is generated, and then inside of this index, the file pointer, so that is the data pointer, and the metadata information is stored. So that is actually software, not hardware. So storage device just provide the data space. So data space for persistent data, and that's it. And then operating system can access the location of the storage devices using block addresses, like logical block addresses called LBA. So actually, the file system should be organized on the storage devices. And then we will learn how this file system can be organized. So actually in this class, we will use the simplified file systems, but this file system is similar to the file system of Linux or Unix operating systems. Unix or Linux operating systems use the inode, that is called the index node. So actually, in order to manage the multiple files, these indexes are stored in some location of the storage devices, and then operating system manage these indexes. So as I explained, some point of the data, and then the metadata information is stored inside of each index structures. Okay, but these software, so these file systems also should be stored inside of storage devices, because you need to remember that storage device is a persistent memory. So persistent memory means that even though the power loss happens, that means that power is turned off, while some crashes happens by some reason, those data should be maintained. Okay, that's why the storage device is different from main memory. That's the DRAM of the computer system. The data inside of the DRAM is removed if the power is off. That's obvious, but these software or some data inside of the persistent memory should be maintained. So we can think that, oh, that's very simple, that it's very obvious. So we can just store the data inside of the persistent memory and that's it. So we can simply think like that, but that's not true. Actually, managing these persistent memory or persistent storage is not easy. It's not simple, because we need to handle some unexpected situations. So while the file system is updated, then the power can be off. Power loss can happen. So we need to also manage this situation. So it's emergency situation, but persistent memory need to support this emergency situation. So recently, some modern computer systems support the some non-volatile memory, like Intel 3DX point. And so also we can use some persistent memory, like also Intel support the libraries for managing persistent memory. So actually, these persistent memories are deployed inside of the server system, and then there's some persistent data such as logs, and then some transaction data, and so this data is stored and managed inside of the persistent memory. But the disadvantage of this persistent time memory is that the performance is lower than the volatile memory such as DRAM. That's why we need to also focus on the research on persistent memory. So okay, so let's start from the file system. So let's learn about the file system layout. So this is some basic assumption of the file system. So it's a file system layout. So first assumption of this is the simplified file system. So we just simplified some many aspects of the Unix-like file system, such as ext2 or ext3. So this is the very simplified assumptions. So file system define a block size. So we learned that operating system manage each location of the storage device as block. So and then operating system just request very simple access command such as read, write, erase based on these block addresses. So in this simplified file system, we assume that operating system just support the fixed sized block. So we assume that the block size is the 4 kilobyte. So operating system access the each data inside of the storage device with the 4 kilobyte granularity. Okay, and you can use this number 4 kilobyte because actually the virtual memory supports the 4 kilobyte of a single page. If we use a very simplified virtual memory system, then we can use the size of the single page is 4 kilobyte. So that's why it's very simple. So if we access the storage device at a 4 kilobyte of granularity, then we can simplify some data movement between these virtual memory and storage devices. Okay, so we assume that the file system has the fixed 4 kilobyte of blocks. Okay, and then the master block. So when we define the structure of the directories and files, I explained that these directories have tree-like structures. So in the tree-like structures, there is a root, the root of the tree. And then so you need to remember that a file system is just a software stored in the storage devices. So in order to access this root of the file system or directory, so we need to know, or operating system needs to know, the location of this root directory. So just to remember that the directory is a list of files or directories on this directory, and then Unix-like file system provides the root directory. This is the highest level node of these tree-like structures. And then how can we access this root directory? We don't know. We don't know if the operating system does not know the location of the root directory, then operating systems cannot access this root directory. And that's obvious. So actually, the location of the master block is fixed in the storage devices. So when we so sometimes we may install the operating system manually, and then people installing the operating system, then we first need to generate the partitions inside of the hard disk drive or SSD. And then this creating partition is some task to manage the disk location, and then with this partitioning, then this partition management tool generate the master block inside of the storage devices. Okay, so this location of the master block is fixed and then is known to the operating system. Okay. Also, in order to store new data, then we need to know the location of the free spaces in the storage devices. So this free space should be also managed by file system. So file system also have information of the free space, location of the free spaces. So this information is also stored inside of the file system. Okay. So we can use the bitmap-like free map management. So in this simplified file system, we assume that the storage devices are partitioned. The storage devices are split into fixed sized blocks. So this bitmap like the premium management structure just indicates which space is empty or which space is already occupied. So it's very simple. So it's a bitmap like file data structure, and then each bit locate a certain block inside of storage devices. Okay. So 0 may represent this space is empty, or even may indicate that that the target space is already occupied. Sometimes we may the operating system may need to manage some specified spaces like swap spaces inside of storage devices. Okay, and then we need to consider these factors when we design a file system. So how to allocate the data, and then how to manage this data with the index files, and then how to manage empty spaces in the storage, and then how to manage some specified space like swap spaces. Okay. Also, I just explained the very simple aspect of a file system, but when we design a file system, we need to also consider performance. So it's the first factor of the computer system, and reliability. Okay, and then some performance overall also is very similar to the performance, and then also the security or permissions. And we need to also think about these factors. Okay, so actually there are many file systems, and then these file systems are developed for specific purposes. Okay. So the first, when we design a file system, so we need to consider how data is organized in the storage devices. Okay. So actually, the storage device it's a very similar to the normal memory, because when you access the data inside of the memory, then we can access this data using address, that is the pointer of data. Okay, and then if we know the address of the data, then we can simply give commands, give a request, you feed this address, and then we can access the data like read, write, with the read write command. So how about the storage? Storage is the block-based memory devices. Okay, so actually the structure of this block-based memory is very similar to the memory, because with the address, with the byte address, we can access the data inside of the memory. Okay, but then with this block address, we can access a certain block inside of the storage device. But how about the file? And how can we organize a file? So in the previous slide, we assumed that storage devices is split into fixed sized blocks, like 4 kilobyte blocks. But we frequently use very large size of files. Like so some files may need to occupy multiple blocks. Then how can we assign these file data inside of the storage devices? Okay, how? So this is the block devices. and then this is a file data, and then the size of this file data is larger than the size of a single block. Then how can we store this data inside of the storage devices? The first approach is the contiguous allocation. So it's very simple. When a certain part of the file data occupies the first block of the storage device like this, then the remaining part occupies the next blocks on the another next blocks like this. This is the contiguous allocation. Okay, so it's very similar to a memory. So actually, in the day, so if you learned about the virtual memory, and then so I believe you already know that the virtual memory space, the text data is stored some part of the contiguous memory space, and then also another static data is stored, and then dynamic data is stored like this, and the stack is stored in the upper part of the virtual memory space. So actually, in the virtual memory spaces, the data is contiguously allocated. Okay, and if this data is a static data, then it's already contiguously stored inside of the virtual memory space, because it's simple, and then it's easy to manage this contiguous memory allocation. But how about the storage? If we can allocate this large file in the storage device contiguously, then we can simply access the first block of the file, and then if the file size is larger than this single size of the block, then we can just access the next block and the next block and next block. It's very simple. It's very simple. If the file can be organized in the storage device like this, and then another benefit is the performance. If the large files can be allocated storage like this, then we can sequentially access each block of the inside of the a single file. And then if the multiple blocks are sequentially accessed, then performance can be high. So performance can be improved so fast. Okay. What's the problem? If we increase the file size, then how can you manage this increasing file size? So if we just if we just want to add more data inside of the file, then if the file size increases, then we need to find another space, that's another large contiguous empty blocks inside of the storage devices. So what's the problem? So inflexible. So with this file management, then the operating system need to find the large empty spaces. Okay. Also, fragmentation problem. So the file size can be changed by users, and then sometimes the file may occupy these small spaces. Also, sometimes the file may need to occupy the large spaces. So in this case, when the file size is updated, then we need to find the appropriate location inside of the storage. Okay, that's another problem. So actually, we do not use this approach. Then another approach is the linked structure. So with the linked structure, and then if the first location of the file is pointed, and then this block has the another pointer to the another block, the next block of a file. Okay, so this is the linked structure. And then if the file size is larger and then or increased, then we can include another pointer to the next block, and then this pointer can point the next block of a file. So this is the linked structure. So if a file size is large, and then or the file size is increased, so if the more data is updated, then we can manage some storage blocks like this. So you can just generate the new link to the next block, and then the new data is written in this new block. This is the linked structure. So with this linked structure, we can reduce the wasted space inside of the storage, like because we just need the one empty space, and then but what's the problem? The file is fragmented, and then in order to access the very last part of the file, then multiple blocks should be accessed again. So for example, let's assume that the file size is the 4 GB. Okay, then in order to access the last part of this file, then we need to access the first block of the file, and then find the next block and the next block, blah 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 blah, and then finally we can access the final part of file. So for the random access of the file, this structure is not appropriate. Okay, if the very large file is randomly accessed or randomly requested in the data of this large file, and then the linked structure, then the performance can be very low. Okay, so sometimes we can use this linked structure for some specific data. So, but if for the general purpose, that we cannot, it's not good to use this linked structure, because sometimes we can access the data inside of the storage randomly. Okay, and then another structure is the indexed structure. So this indexed structure means that the file system has some index structures, and then this index block has the multiple pointers to the multiple blocks of file. Okay, so a file occupies the multiple blocks, and each pointer of this multiple block is stored in some array structures inside of this index. And then if the file size is larger than the supported file size of a single index structure, then we can generate another linked index. And then this index is also pointed by this root index, and then another index has the multiple pointers of the blocks occupied by a single file. Okay, so in this indexed structure, each file has the index structure, or it's called the inode, and then this file information or metadata is managed inside of this indexed index structure. Okay. Okay, with this indexed structure, we can handle the random access better, but and then still good for sequential accesses, because if a file data is sequentially accessed and requested, then we can just get some multiple pointers inside of this indexed structure, and then with this multiple pointer block logical block address, we can access the location of the blocks inside of the storage. Okay. So modern file systems usually use the indexed structure. So and then actually the Unix file systems such as ext 2, 3, or 4, then these file systems use the indexed structure. So it's called the inode. Then let's talk about the Unix inode. So inode is the abbreviation form of the index node, actually. It's the then we can simply call the index node as inode. Okay. So this is the index structured file system, and then each file, if we generate a file, then the inode is assigned for each file, and then the file information such as the protection, timestamps like the access time, and then the file size as length or some another metadata is stored inside of this inode data structure. Okay. Also, each inode contains 15 block pointers. So this is the indexed structure, indexed file system. So inside of the inode, each inode can store 15 logical block addresses that points the location of the disk or storage devices. Okay, and then if the file occupies the multiple blocks, then we can use this multiple pointers to the logical blocks inside of logical block of the storage devices. And then, but the file size can be large, so a single file can occupy more than 15 blocks. So in order to support this situation, some block pointers can point the another location of the file, and then in this location only stores the pointers for the block address, the next blocks. So we can organize this large file with the hierarchically. So you can this pointer points the another blocks, and then this block includes the multiple pointers, and then multiple pointers also can point some another blocks. Okay, like this data blocks. Also, this pointer can points some another block pointers inside of the storage. So we can organize this large file with the hierarchical block pointers inside of the storage. Okay. So inode is not directory. It's a data structure, and then it's a data structure to manage a single file. And then directory is the data structure that manages the list of multiple files. Okay. So inode is some specified data structure that is designed for managing multiple files. And then as I explained, so inode also has information about the pointers of multiple blocks inside our file, and then this information is managed inside of the inode. And then directory is also a kind of a file or kind of a data structure that includes the file name and then location of the file. Okay, that is the inode number. So inode, so the a Unix inode can refer a file. Also, the inode can refer a directory. Okay. The file is actually a data. Directory is also a data structure. So in the Unix file system, directories are also managed like a file. So that means that each file has its own inode number. Each directory has also its own inode number. So we use the ls command, then we can check the inode number of a directory. Also, we can check an inode number of a file. Okay. Okay. So these are metadata used in the Unix file system. So this is is a file. This is file information, and then inode data also manages this metadata information inside of the. So this metadata information is stored inside of a inode. Okay. You can find some several data like the ID, the inode number, protection, like blah 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 blah. Okay, block size or block count is here. Also, you can find the user ID, the owner of the user ID, and then owner of the group ID, like this. Then we can also find the access time here. The last access, last modification, last status change is here. So this data is stored inside of the inode. So like with this data structure. So when the file is created, then the operating system, the Unix-like operating system stores this metadata inside of the inode. Okay. So if we generate a file, like so in this example, I generate a file named file inside of a workspace directory. Then if we use the command stat, it's the Linux command, but Linux is very similar to Unix. If we use the stat command, then we can find the metadata information of a file. So stat command just access the inode of a file. And then stat command just read metadata inside of an inode, and then just print out the metadata. Okay. So we can find the name of a file, then size, then how many blocks are occupied, and then the size of the blocks, and then file type. So it's a regular file. And then this is the inode number of a file. Okay. So this is the device ID, then permission, UID, GID, then access times here. And you can, so what is the link? So this is the link for the data. So I explained that the inode is the index structure. It's the index structure. So that means each inode is indexing a certain location of data blocks. So for example, if we generate a file, then the data is stored inside of data blocks in the storage, like here. And then a certain inode is also created. And then we operating system assign an inode number for this inode. This. But we can also create another inode that indexes same data block in the storage system. That's possible. We can just generate another inode block, inode structure here, like 957 and 1109. So another inode number. And then this another inode number can index the same data blocks. Okay, then this link represents the number of inode blocks connected to this data blocks. Okay, because this is just on index. Okay, index is just some reference to the data location. So we can generate multiple indexes in the software, right? So that means we can also generate multiple inodes that reference the same data blocks. Okay. And then if we just use the stack command for directory, like workspace directory here, you can find, oh, this is a directory. So we can find that, oh, the inode number assigned to the directory here, so links are 2. So that means that this directory has the 2 links. Okay, 2 links from the inode. Okay, so we can find some metadata information here. Those like because it's a hard links. So in this slide, I explained that multiple inodes can reference a single data blocks. So it is because the inode is an index. So that means the same data can be indexed by multiple indexes. And then if these same data blocks are referenced by multiple inodes, and then we call this link for the actual references to a single data blocks is called the hard link. So in the Unix file system, we can generate the hard link using command ln. If we just use our ln command, and then we generate, and then we can generate a hard link for the same file. Okay, so for example, we can generate the file like called A. Then we can generate another link B for this file A. If we just use the ln command, then that means that the Linux operating system just generate the inode, another inode, and then this inode just index the same data blocks of another the file A. Okay. So this is called the hard links. So how can we create a hard link? So under this workspace directory, I already generate a file called file here, and then I generate the hard link using ln command here. So then some file 2. So if we use the ls command here, ls and -i command, so -i option, -i flag of the ls command just shows the inode number of files. Okay, so if we just check the inode number of file and file 2, so we can find the same inode number is assigned to the file and file 2. Okay. Okay. If we just use the stack command here, then we can also find. Oh, that means that is just the link for the file. Sorry. I just confused. So if we just generate the hard link, then the new inode is not generated. Just the same file is referenced by directory. So in the directory, the file name is generated, and then this file is connected to the same inode. Okay, but the file name can be different. So I was confused. Sorry. So if we just check the inode number here, then same inode number is assigned, but we can find that multiple links are generated for this file and file 2. So that means that, so actually this is the same. So it's the same. So inside of the directory, if we use the ln command, just use the ln command, the file, this list is just added inside of a directory. So actually this directory already has a file mapped to the inode number 9571118. And then if we use the ln command, so it generates the hard link, then another entry is created, and then this new entry has the file name file 2, and then inode name, same inode name is registered inside of a directory. Okay, so hard link is just generate a new entry of the file inside of a directory, and then this new file, so actually new file name, just connected link to the same inode. Okay, so it's just a file name. Sorry, it's the same inode, and then this inode is pointing it's a block, but this inode is referenced by file and file 2, and then this information is stored in the directory. Okay, so if we use the stack command, then actually the inode is the same, so the same information is accessed like here. But soft link is somewhat different. So we can generate the soft link with the ln-s. So this, if we use the -s option, then this ln command can generate the soft links. Well, it's called the symbolic links. Okay. So this link is just another file. It's a file. It's a new file. So if we use the ln command, if we use just a ln command without any option, and then this ln command just generate a list of another file that references the same inode. Okay. And then this new entry is created inside of a directory. But if we use ln with the -s option, it means the symbolic links, then this ln command just to generate a new file. So that means that with the ln -s option, the new inode is generated, and then this file is a new file. This file just points the some original file, okay? Because so this symbolic link just has a data. This is the information of a target file, and then this data is stored in the data blocks inside of the storage, and then this new inode is referencing this new data block, okay? This is called symbolic link. So in this slide, we can generate a symbolic link with the -s option. Then if we just check the inode of these two files, the file and file 2, then we can find that the inode number of this file 2 is different. So we can find that the number of links for this file is 1, and then it's 1, because this is a inode for file. And then if we use the -s option, then new inode is generated, and then this new inode is pointing file 2, so another data block. And then inside of this data block, there is a link to this file. Okay, so symbolic link is just a file. Okay, it's just a file. But if we generate the hard link, then that means that the new file is generated, but this new file is also referencing a same inode. So that means actually the same file. Okay. Okay. So now, I will explain about some simple implementation of the file system. But it's a new another some topic. So let's take a break for 10 minutes before the next topic. So I will be back at 11:42. Okay. Okay. So it's getting cold recently because recently the weather has been cloudy. So sometimes I feel cold. So actually the weather in Korea is very change quickly. So sometimes it's not good. Okay. So now, let's see how these file systems are located in the block-based storage devices. So actually, we learned that the file system is just a software that manages that is composed of a data structure, and then in the Unix-like file system, the Unix just generate the inode, that is the index node. So that is just an index for a file. So it's the index for data block. So that means if a file is created, so we can easily create a file. Okay, if a file is created, then the inode is assigned, and then the file information is stored inside of this inode, and then inode has some block pointers for file data and then metadata information of a file. And then, so we learned that. Also, this inode has the information. So actually, I also explained that directory is a data structure that is just a list of file and connected inode numbers. And then the directory has the also its list of files on the uncertain directory. Okay. So and then let's see how the files are located on the block-based storage memory. Okay, so block-based. So in this example, we assume we assume a very simple file system. So let's assume that we are designing a file system. So this is software. So let us assume that we are designing a very simple file system, but this file system is very similar to the file system of Unix operating systems. Okay. So this is the storage devices, and then the storage devices is split into multiple blocks, and then let us assume that this storage device has fixed sized block. Okay, and then the size of the single block is 4 kilobyte, and then let us assume that there are total 64 blocks in the storage device. Okay, so we can just split the storage devices like this, and then each block number is assigned from 0 to 63 because there are 64 blocks. And then when we create a file system, so that means that the file system just manages multiple files and directories. And then this is very simple file system is similar to the Unix file system. So that means that the file system is the inode. So inode is just a data structures. So we need to also store these data structures in the storage devices. So we split the blocks of storage device two part. Is the some special part. so inodes are also stored inside of the block, inside of a storage device. So we just assign a storage space for inodes. Okay, and then the remaining blocks are assigned to the data, so file data. So we assigned 56 blocks for data region of this storage device, and then we assign 5 blocks for inodes. Okay, so please note that a single inode can reference multiple blocks if the file size is large, right? So, but we cannot, this is the very simple file system. So we just fix the size of the data region. Also, we just fix the number of blocks assigned to the inodes. Okay. So in this inode region, the only inodes are stored. So let us, if the size of a single inode is 256 bytes, we can store 16 inodes per block. And then 5 blocks are assigned to inodes. Then we can have totally 16 multiplied by 5 is 80 inodes. So in this file system, we can create total 80 files and directories, including directories. So we can just create the 80 files or directories with this file system, because only 5 blocks are assigned to inode. Okay. And then also we need to manage the free blocks of this storage. So we need the free list of the data region. Also, we need a free list of inodes. Okay. So for each inode number is assigned inode number. So, and then I explained that there are only 80 inodes in this inode block. So that means that we can generate the total 80 files or directories. Okay. Now, if we delete a file, then this inode has no data for files. So inode is empty. So we can also assign a new file for this inode. So we just need an information about the free inode. Also, we need the list of the free blocks in the data region. So there are 2 free lists. So the first free list is the free list for the block, the list of free blocks in the data region. Also, another free list is the list of free inodes in the inode region. Okay. So let us assume that this free list has the bitmap based structure. So for each block for the data region, if the block is occupied, we can assign 1. And then inode is the same. If the inode is already occupied, we can assign 1 for a certain bit information. And then super block. So this is the super block. So let us assume that the super block is located in the first block of these storage devices. So that means that this super block has the information about the file system. So that means so if we create a new partition in the storage devices, that means that a new file system is created, and then this information is stored in the super block. Okay. And then let's see the blocks that includes inodes. So we already learned that in each block, 16 inodes are assigned. So in order to access a certain file, let us assume that the file name is A. Then the inode for this file is also assigned. So let us assume that the inode for this file A is 25. Okay, it's inode number. Then how can we access this file? In order to access this file, the operating system needs to access inode first. Okay, the linked inode. Then that means we need the location of this inode. Okay, so actually this information is already known to the operating system. Okay, so inodes are occupied. Inode has fixed size like 256 bytes for this example, and then each inode nodes are assigned for each location inside of a block. So inode 0 occupies the 256 byte, and then inode 1 occupies the next 256 byte space, and then the inode 2 also occupies the next 256 byte of space. So based on this inode number, the operating system can access the target inode. So if the inode number is 25, then this inode is located in inode block 1, because so only one block includes the 16 inode, and then in the inode block 1, the 55 is here. So operating system can read the data structure in this inode number 25. Okay, so with this inode number, the operating system can locate the location of inode. Okay, and then as I explained, the inode has this metadata for file. Then this is the example of ex2 inode. Okay, so we can find the size of the data here, and then the name of the data here, and then also the definition of this data structure. Okay, so metadata is stored in the directory. Directory is just a list of a file, like file name and inode number of a file is linked. So this list, this entry has the file and the linked inode number, and then this information is registered in the directory. So this is the content of the directory. Like, so you can find that the inode number here, and then it's the string length. So because the directory has a file name that is the string data, the string data, the string data, the string data may have the various lengths. So this length is also stored, and then this is the allocated lengths, allocated lengths inside of the directory. So it's the allocated length of the file name. Okay. So what does this mean? In the Linux file, in the Linux system, that means the current directory. So actually this dot is referencing the current directory, and then two dots dot represent the parent directory. So this information of the parent directory is also stored. The current directory and parent directory is also registered inside our directory. It's a data structure. So you can find the inode number of parent directory is 2, and then string length is 3, and then this can be file or directory. So we can find that inode number for this foo is the 12, and then inode number bar is the 13, and then this very long file name, like so inode number is the 24 is assigned. So we can find that the string length here and here. So and then for this long file name, more space is assigned inside of the directory. Okay, just a list of files or directories. Okay, and free space management. So the file system also manages this free system. Okay, that means that we have two kinds of free list for the one list is for free blocks, free data blocks, and then one list is for free inodes. Okay. And then in this simplified system, so we just assign the bit for each block, data blocks, and then each inode. Okay. So let's see how the file system is accessed. So that means that the data, the storage device is accessed when a file is accessed by application. Okay. So let us assume that this is the read process, and then we assume that an application try to read file var on the full directory, and then let us assume that we need to read 3 blocks of a file. Okay. So how can we read a file? So in order to read a file, so we need to first open a file. Okay. So if you are familiar with the C, then you can know that in order to access the file, we first need to open a file with the fopen command and fopen function. So first, when the file is accessed, we first open a file and then access to the location of a file. Okay. Then we need to first open a file, then we first read the root inode. So in this path of a file, we can find, oh, this is the root directory. And then under the root directory, there is a directory named foo. And then under the foo directory, there is a file named var. So here, so when a root directory is accessed, the operating system just scan the list of files or directories on the root directory, so we can find the inode of foo. Okay, because the foo directory is connected to the inode of foo, and we can access the foo directory. Okay, but in order to access this list, then we need to first access the inode. So it's a read command. So it's a read block for the storage. And then we need to read the data blocks indexed by this root inode. Not to access the directory, the list of files or directories. Okay. Or we get inode for foo from this root directory. Then we need to read the inode for foo directory. Okay. This inode, the inode of foo is referencing the data blocks of foo. And then what data is stored? The directory list or file list are stored the data block of foo. So we need to read the foo data here. And then inside of the foo, so foo, you can find the inode of var, right? So we need to read the var inode. So we need to access the var inode of var. And then this, we assume that we need to read the 3 blocks of this file. So that means that in the inode of var, so there are 3 logical block addresses that is linked the data regions occupied by var. So we need to first read the var inode. in order to get the logical block address for the first block. And then read, and then read, write. Why do we need to write the bar inode? So for this first read, we need to get the logical block address of the first block, and then read this logical block address, we read the bar data 0, and then, oh, so bar is accessed, so we need to update the inode also. Why? The file is accessed, so we need to modify the some access timestamp of the inode of bar. And then read, write, read, write. Okay, so how can we know? Not to read just 3 blocks of a file, then operating system needs to access storage devices. How many times? Wait, 1, 2, 3, 4, 5, 6, and then 3 for the first read. It's a 9, and it's a 5. So we need to access 14 blocks of storage devices. So we want just 3 blocks of a certain file. But in order to access read the 3 blocks, then we need to access storage devices 14 times. Okay. So, but you know, if the data is accessed, then some data of the storage devices can be cached in the main memory. So we can use the cache mechanism to reduce the data accesses to the storage devices. Okay, but if the data is not stored cached in the main memory, they not access the actually not to read the 3 blocks, then we need to access 14 times the of storage blocks. Okay, so it's a very high overhead. Okay, for the right, it's more storage accesses are required. Okay, so it's the full bar, and then reduction, then we need to write the 3 new blocks to the storage. So we need to access the root inode, then root data is read, the full inode, full data is read. Oh, then we need to write a new file. It's a bar. So the first, in order to create a new file bar and then store data inside of a bar, we need to first find the empty inode, because this is a new file. And then if the new file is created, then new inode is assigned. Then the operating system need to find an empty inode. Okay, so we need to read the inode bitmap. It's a free list, and then write inode bitmap, because we need to update the inode bitmap because the new inode is assigned, and then this inode number is assigned to a new file. And then because the new file is created, then this new entry is registered inside of foo directory here. Then we need to also update the data blocks of foo directory. Okay. Then the inode is generated, so we need to read inode bar inode and write. It's a new file, so we need to write the new data, and then also the directory is accessed, and we need to update the foo inode. Okay. So, and then in order to write a new block, new data to the blocks of storage devices, then first access the var inode. Oh, we need to find the empty space, empty data blocks in the data region, to read the data bitmap and then update the data bitmap, and then write the data to the empty blocks, and then write the var inode. We need to update the timestamps of the var inode here. So for each one block write, we need 1, 2, 3, 4, 5, 5 storage accesses. So 5, 5, 5. And then in order to create a new file, we need to access the 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 accesses. So in order to write a new 3 blocks on the storage devices, we need to access the storage devices 25 times. So overall, the storage access is higher than the file read, like so compared to the 14, the access times for this number of accesses in order to read the new file to the storage device is 25. It's just 3 blocks, so 25. Okay. So actually, the file access is the very heavy performance burden. So we in order to access the main memory, the address translation is required, but this address translation is supported by hardware, so the memory management unit. So in order to accelerate this address translation, the hardware also supports some hardware components like TLB or some memory MMU, some memory management unit. But file system is just is managed by operating system. Okay, so also the storage devices are fully managed by operating system. So actually, this file system requires the many IOs, many additional IOs for block reads or block write. Okay, by providing some abstractions, it's very convenient to users. But in order to support this abstraction, the file system requires the additional input and outputs to storage devices, and then this is the very heavy performance burdens. Okay. It's right. So no access with the 3 blocks, we need the 14 storage accesses. And just remember that storage is very slow devices. Also, in order to write the 3 blocks of data, then we require 25 storage accesses. It's a very high performance overhead. So in order to reduce this performance burden, we can apply the caching or write buffering. Okay. So when the storage is accessed, then the data can be moved to the main memory of the computer systems, and then actually the operating system runs on the processor. So that means that when this inode data is accessed, well, is read, then this data is transferred to the main memory of the main memory. Okay, and then this data is also processed by CPU of this actual operating system. Okay, so CPU. So this data can be cached inside of main memory. So it's because the main memory is faster than the storage devices. So for example, very frequently accessed part like root inode, so or some root data or some super blocks can be cached inside of the main memory. So this can be managed by operating system. So if this frequently accessed part is cached inside of the main memory, then we can reduce the number of accesses to storage devices. Okay. Also, write buffering. So if you see the this part, so we can find that for this part Inode, it's the same data structure, but in the same block. So we can find that frequent read write read write read write read write to the same data structure. It's actually the same data structure in the same storage blocks. Okay. So in order to instead of write the multiple times, you can just merge these write request, and then you can just generate the one write request because it's just update. So this update can be done in the main memory, and then the write request can be merged, and then the write to the storage devices can be done only one time. Okay. So we can apply the write buffering, so the write merge techniques for this frequent write to the same blocks, because in order to reduce the read write input outputs for the Inode data. But what's the problem? So you need to remember that this is the persistent storage. Okay, persistent memory. Actually, the file system should be stored and maintained inside of the persistent memory. So, but for this write buffering, the write transactions are buffered inside of the main memory, and then this is the delayed write to the persistent memory. Okay, what's the problem? This write request is not performed yet. It's not stored in the storage. But if the power loss happens, then this request will be lost. So that's the problem. Okay, so data loss by crashes or power loss. So not to increase the performance, we need to use the write buffering or some delayed write to the storage devices, because storage device is very slow. But not to support this technique, we need to sacrifice some, what's that? It's a persistence of data. Sometimes the data can be lost, then the file system can be corrupted. Okay. Okay. So data loss can happen when the power loss happens. That's the problem of this technique. So that is the trade-off. So in order to increase the performance, we can sacrifice some persistence or reliability. Then for high reliability, then we can sacrifice performance of a system. Okay, this is the trade-off, and also this is very important research area. Okay, in order to support the high performance and more reliable systems, so then we need to also create very fancy ideas for the persistent memory, and also some it's a very important research area in the computer systems also. Okay. So for the performance, in order to increase the performance, then we can also apply some several techniques like a read ahead, which is very similar to the pre-fetch of the memory system. So the read ahead means that the operating system may know when the next blocks will be accessed. So actually, for example, what is the prefetching? So with the prefetching, the computer hardware just monitors the memory access patterns, and then based on this history of memory access patterns, the computer hardware predict the next memory accesses, next memory request. And then based on this predicted memory request, the computer hardware create the data request to the main memory. And then using these prefetching techniques, that we can reduce the data fetch latency from the main memory, because the data is, if the data is requested here, then we need to wait. It's a very long time, but if the data is requested here, then we can reduce this very long memory access latency. That is the prefetch technique. So these similar techniques can be applied to the file system. So actually, with this file system access, then we already expect that, oh, when this inode is accessed, then some data part, data region can be accessed quickly, quickly. So even though this data read is happened, then or requested, then the operating system generate the accesses for data region before the real request, and this technique is the read ahead. So very similar to the prefetch. Okay. And then, so like the prefetch technique, the file, if the data is read sequentially, then also we can generate the next request with a high probability. Okay, so it is very similar to the prefetch technique. Okay. Okay. So in this time we learned about the file system of the Unix-like operating system. Also, actually this file system is widely used for different file systems. So there are many different file systems actually, but this I know the Unix-like file systems are frequently used for any other different file systems. And then so for this Unix-like file system, we use the index structure called inode, the index node, and then based on this index node, the data blocks of the file are accessed. Okay. Then what is the disadvantage of this indexed file structure? In order to access the data regions, then we first need to access the index structure, and then it will create more input and outputs to storage devices. And then storage devices are very slow compared to the main memory. And then this is the very high, very heavy performance burdens in the computer systems. Okay. So actually, the operating system needs to reduce number of accesses to storage devices, because storage devices are very, very slow. Okay. And then also we learned how the data regions and the inode regions are allocated on the block-based storage devices. Okay. So what is missing? What is missing in this part? This is also very simple abstraction. So what does that mean? Operating system handles a storage device like memory. It's a block-based memory. So in this example, we just check the number of accesses to storage, but the access latency to storage can vary. What does that mean? So if the storage devices are just a block-based memory, what is the feature of this block-based memory? The access latency for different blocks are the same. It's just the memory. So if we assume this is a memory, then the data access latency for different addresses can be similar. That's our assumption. That is also operating system's assumption to storage devices. But we already learned that this assumption is not true. For example, the hard disk drive, the access latency can vary based on the location of blocks, like sectors. Okay. So with this file system abstraction, the OS think that, oh, storage is the persistent memory, the block-based memory, and then the access latency for every block, the different blocks are the same or the similar. But it's not true. The latency can vary based on the situation, some scheduling algorithms, or and then some location of the blocks, but this is not revealed to the operating system. And then that's also same to the SSD. So we will learn about some unique feature of the flash memory, that is the storage media of the SSD. But if we learn about the unique feature of the flash memory, then this access latency to a certain physical block can be different. Also, and then these features are not revealed to the operating system because this is the hardware part or some storage part, and then this information is not revealed to the operating system. So operating system just access the storage devices using logical block address. That's it. But in reality, the performance can be different based on the logical block address, and then some access patterns, and then like request from the operating system. So the file system can be developed considering the features of storage devices. So some file systems are also developed for some different types of storage devices. For example, F2FS is the flash-based file system for flash memory-based storage devices. So it is also consider the unique feature of the flash memory, and then applies some unique features for supporting some these features of flash memory. Okay, so this feature is missing in this part. That's the disadvantage of the abstraction. So with the abstraction, we don't need to consider some very complex operation or complex part of the underneath hardware or underneath systems. But if the some devices are too simplified, then some features are the performance can be degraded, so some features can be missing. Okay. Okay. So actually, I also prepared the flash memory. So I think we need to learn the flash memory. So actually, in this course, we will learn about the SSD, and then SSD use the flash memory as the storage media. So in order to understand the architecture or structure of the SSD, we first need to understand the unique features of a flash memory. So actually, I plan to teach these features of the flash memory today, but I think it's a little bit late. So okay, so let's discuss about the features of the flash memory in the next class. Okay, and then also I provide some reading list for these file systems and then flash memory, and then also I will post the some reading materials on the Blackboard. Okay. Yeah. Yeah, I will stop here. Do you have any questions? Okay. Thank you for your attention, and then see you in the next class. Bye.